Okay, the next thing I want to talk about is subnetting. Now, subnetting is the process of breaking a larger network into smaller subnetworks. All right, so talking about networks in general, there are three classes that we have in use today, class A, B, and C. All right, there's class D and E as well. D is for multiclass groups, and then class E is reserved for future use for R&D, so on and so forth. All right, so we have A, B, and C. Class A networks are for very large organizations, 16 million hosts per network. 127 networks, or 127 of those Class A addresses, exist. Class B networks are for medium-sized organizations, 65,000 hosts per network, and there's about 16,000 of them. And then for Class C, we have small networks, small to medium-sized networks, 254 hosts per network, and there's 2 million of those. Okay, this is all referring to public IP addresses. All right, we also have something else referred to as the private IP address range. Each class of IP has its own private IP address range, meaning it has a range of IP addresses that can be used internally that don't route out to the internet. So that means we can have 100 or 1,000 or a million different companies, all using the exact same IP addressing scheme as long as it's within this private range, and they don't step on each other, okay, because it never routes out to the internet. That's defined by RFC 1918 for IPv4, and by RFC 4193 for IPv6, or IP version 6. All right, now as I said, they're not routable on the internet, and it's for private use, internal use only. All right, so it doesn't matter if multiple companies use that same space. As an example, the 10 space what we have here. All right, so each range we have class A's that use the 10 space, 10.0.0.0 through 10.255, 255, 255. We have class B's, as you can see, and then class C's. So each of those is a private range, and you're probably familiar with the 10 space or the 192 space. That's typically what's used in most networks. Okay, so not to bring back too many harsh memories for some of you. This might be pleasant memories for some. It could be a nightmare for others. But picture this being a high school or perhaps a college cafeteria, right? Where we have hundreds or maybe thousands of kids in in one room, all talking about whatever there is they're talking about. Imagine trying to have a conversation with someone 4 or 5 tables away. Right? There's just too many people talking at once. You have collisions, basically, people talking over top of each other. Very hard to understand, right? It's also very insecure because everybody can hear what everybody else is saying as long as they're listening. All right, so that's kind of the same concept when we're talking about subnetting on an IP-based network. We don't want to have 5,000 hosts in one network, just like we don't really want to have 5,000 kids in one cafeteria if we want to have a very efficient use and be able to communicate very efficiently without having to repeat ourselves over and over again. All right, so if we turn around and we did it separately, where we kind of segmented this out and created smaller rooms, smaller cafeterias where we have fewer students in each room, then it's quieter, right? There's less collisions, there's less people talking over top of each other. And then you can have a more secure environment as well, because people in one room can't listen in on what's being said in the other room. All right, so we reduce our collisions, basically people talking over each other, and we also increase our security. So the same concept applies when we're dealing with subnetting. We're going to break a large network into smaller subnetworks. All right, and as I talked about, it reduces congestion, it improves the flow of traffic, and it also can increase security. So here we have one big giant network. We have lots of computers, right? Hundreds or thousands of hosts. Well, what we want to do is get away from having one big network with lots of a lot of traffic rather, and lots of collisions, and also limited security. We'd much rather have a more secure network and break it into smaller subnetworks by reducing congestion, improving that flow of traffic, and increasing security. All right, so in doing that, we break that into 2 smaller networks, and you'll notice we have a router in between the two, and by having the router in place, as we've learned from a previous video, we can increase security because we can set access control lists on that router and basically list out or control who can talk from one network to the other. So on an IP-based network, we constantly have collisions, and the more hosts we have on a network, the more those collisions will occur. All right, and it makes the overall network much, much less efficient. So by breaking it down into smaller subnetworks, we increase the efficiency. Okay, so here's a subnetting example. All right, we have a Class A network, 10.0.0.0. All right, too large for one giant network. All right, so Class A could house possibly 16 million hosts. All right, way too big. So what we want to do is we want to subnet that into smaller networks, and we're going to borrow bits from the net mask or the subnet mask. So in other words, an IP address, an IP version 4 address, is 32 bits long. All right, so we have 32 bits to describe the network and also the host. Just like you have a house number and a street address. There can be many houses, right? 1, 2, 5, 10, 15, 20, whatever your house number is, but you all live on the same street. Well, that's what a network mask and a host address is, okay? So you have the house number and the street address, so to speak. So those bits, you can borrow or you can slide them left to right, which we'll see in a moment, that will basically break up our street into smaller streets. All right, so 10.0.0.0/8, it's too big, all right? That's a standard class A network. You can see that the ones in that first octet, that defines the network. So what we're going to do is we will borrow bits, we'll borrow those zeros, and put them from the host addresses, or from the host space, into the network space. So that way, we now have 24 bits that define the network, and only 8 bits that define the host. All right, so that gives us basically a lot of subnetworks within that 10 space. Less hosts per network, but more subnetworks to deal with. All right, so again, here's the example. 10.0.0.x/8, okay? 8 bits for our subnet mask. The ones in orange, that's going to be our host address. Down at the bottom, now we're going to subnet, and we're going to make it 10.xxx/24. So we're borrowing bits from the host, we're putting it into the network. So now we have all of that space available for the network. So you can see network hosts. We're sliding the network now over to the right. So we have more networks, fewer hosts. In the up above example, we have fewer networks, more hosts. So if you take 2 to the 8th power, that gives you 256, which is really 0 to 255, since we're starting ordinally when we count, dealing with binary information. So we start at 0 through 255. We can't have our host address be 0, and we can't have our host address be 255. 0 defines the network, 255 defines the broadcast ID in this example. So we're left with 1 through 254. So that actually gives us 256 IP addresses, but only 254 of those are addressable for hosts. So on this Class A example that's been subnetted down to a Class C, we only have 254 hosts per network.